In this video, we're going to examine how the properties of logs come about. If you recall, logs are really just exponentials written in different forms. So for our first exploration here, notice how we have a lot of different bases of logs, but they all have log 1 basically. So if we rewrite these as exponentials, remember that we can write them as 5 to the x equals 1. In this case, we would have 2 to the x equals 1. Notice how our exponential is always equal to 1. 10 to the x equals 1. And remember, this is really like a log base e. So what we're saying is e to the x equals 1. Now, one thing you know about exponents is anything to the 0 power equals 1. So this value is 0. Anything to the 0 equals 1. That's 0. You can see that this just repeats. We're just basically seeing how this property comes about. So basically, you can see here that if you ever have log of any base, it can be any base at all, log base a of 1, you'll always get the value of 0, no matter what. Similarly, looking at e through h, you can see here that if we rewrite this as exponentials, we have 5 to the x equals 5. Well, it's the same number, meaning that the exponent must be a value of 1, right? So 2 to the x is equal to 2. Again, same number is there, meaning exponent must be 1. So this property always holds true, right? 2 to the first always equals 10 to the first always equals 10. And in this case, this is a base e to the first also equals this value of e as we do the loop trick. So we can see here that we always have the same property here. If that base and that number is always the same, log base a of a, then you always get a value of 1. Exploration 2. Let's take a look at how the inverse of a function may be combined with the original function. So in this case, we have g of h of r. Let's take a look at what g and h are. So g is log base a of x. So we're going to say g, the outside function, is log base a of whatever x is. But in this case, x is now going to be the h of r. H is the a of x. So we have a to the power of, well, our input is actually r. So that's what we're going to write here. That's g of h of r, log base a of a to the r power. Now, one thing you can see here is if we don't know what this value is, let's call it x, we can see that a to the power of x is equal to a to the power of r. And look at that. They have the same basis, meaning that x is equal to r. Our entire x, this entire thing, the entire composite function, is equal to r. Okay, so that's what we can see there. That is basically our property number 2. You can see log base a of a to the r is going to equal r. Going over to b, h of g of m. Let's see, h is the outside function. That's a to the power of something. What's that something? That something is g of m. So here we have our g function. So a to the power of log base a of x. Okay, and one thing that we had seen from a previous section was if you have a to the power of log base a, notice that the exponential and the log are inverses of each other, and they end up canceling each other out. And what we're left with then is just an x. Or I apologize, this is not x. That x value was technically the input of m. So all we are left with is just m. So we can see our property number 1, a to the log base a, cancels each other out, and we're just left with m. Now going to exploration 3, let's take a look at how we can do the 4 basic operations with logs. So here we have log of 100 times 10. What is that? That's log of 1,000. Log of 1,000 is equal to log of 100 plus log of 10. If we actually find each of these values, we have a base 10. 10 to what power is equal to 1,000? That number is 3. This is going to be a value of 3. 10 to what number is equal to 100? That value would be 2. And 10 to what number would give us 10? That value would be 1. What we're seeing is that 3 is equal to 3. We are showing that this particular property is true. Okay? As we take a look at b, we have log of 1,000 divided by 100. 1,000 divided by 100 gives us the value of 10. We know that on the other side we have log of 1,000 minus log of 100. And if we find each of these values, remember these are all base 10s if there's no number written there. So 10 to what power equals 10? That would be 1. 10 to what power is equal to 1,000? That would be 3. 10 to what power is equal to 100? That would be 2. So 1 is equal to 3 minus 2? Yeah, that is 1. So we also see that this property also holds true. Okay. And lastly, let's look at letter C. Log of 10 to the third power. 10 to the third is the same thing as 1,000 equals 3 times log 10. What is log of 1,000? Well, we're technically saying that that's base 10. 10 to what power equals 1,000? Well, that's just 3. And so we have 3 is equal to 3 times 10 to what power equals 10? That'd be a value of 1. So 3 equals 3. Yep, that works out. So this is also going to give us a true statement. What are these three properties telling us? We're in some way trying to find out how, hopefully what you're seeing is a connection that there is 100 here, there's 100 here, there's a 10 there, there's a 10 here, but the operation involved is multiplication inside the parentheses, and outside the parentheses we see addition. Over here we have division contained within parentheses of our number 1,100. Here's the 1,100. And outside the logs we see that there's a subtraction symbol. Okay. And then lastly, what we also see here is that there is an exponential, an exponent here, and somehow that exponent got brought down to the coefficient. Let's take a look at our properties of logs now. So, using those three examples, what we can say now is that if you actually have an m times an n, right there, log base a, it doesn't matter what base it is, but if you have two numbers being multiplied within the log, you can actually separate them into two separate logs. Log base a of m plus log base a of n. You can separate them into two separate logs like that. Log base a of m divided by n, if you need to recall, you can always go back to the previous page, but the property that you now see is that when you see a division sign contained within the parentheses, you can again split it up into two separate logs. Log base a of m, and then you have minus log base a of n. Okay? And then the last property we have here is that if you do see an exponent, and you can actually bring that exponent down as the coefficient of your log. So we would get r log base a of m. Those are equivalent values.